Yeah, okay, working. Let me begin by recapping various approaches discussed so far. So recap. Approaches to do quantum mechanics. Well, the first one was non-relativistic quantum mechanics. Here you have Schrödinger theory, where you solve the Schrödinger equation for the time evolution of the state vector. Time and space are treated unequally. Time is a parameter, while x is an operator. And this is what one may call a space-time approach. On the other hand, the same quantum mechanics can be described using a path integral approach, where one calculates the matrix element which is given by integral dx. So x is a three-dimensional Cartesian coordinate, e to the power I by h bar SIF x vector, where S is given by integral Ti to Tf dt L x x dot and t. And this is a world line approach. Now, example, we studied the explicit working out free particle and harmonic oscillator. Okay. Then we studied relativistic quantum mechanics. In this case, both time and space are lifted to operators. And x hat, it's a four-dimensional coordinate x, four-dimensional Cartesian coordinates. It represents an event, and it is because of that operator that we have a state with a level which is leveled by 4x. This is what we did is that the approach that we discussed using path integral, which is a generalization of this statement, and the generalization actually involved certain geometric views. That is a world line approach. So this is a word line approach, and the result and the path integral. The question that one asks is the matrix element xi xf xi, and it is given by dx from I to f d lambda over v e to the power I by h bar s I f x comma lambda, where this is given by action is given by integral d s 0 to 1 Lagrangian x dot lambda. Okay, so this is obtained from this using some geometric considerations. And we have an internal parameter s, S is an internal parameter and it's unphysical, and there is a reparameterization invariance this looks like a symmetry. However, the parameter associated to the symmetry is not a physical parameter, so it's not a physical symmetry. It actually indicates that there are redundant degrees of freedom. There are degrees of freedom. There are configurations which look different but actually physically equivalent. And it is because of that that we have to divide by the corresponding gauge volume, divide the path integral by the corresponding gauge volume. And here we considered the example of a free particle. This geometric consideration, applying geometric consideration to get that Lagrangian, this worked for a free particle. We have not considered anything that has interactions, and for a free particle, the result is given by xf xi free. We calculated it last time. It's given by dE 0 to infinity I alpha pi h bar e whole to the power minus d by 2 times exponential I over alpha h bar xf minus xi whole square over e minus e mu square. Here alpha and nu are parameters in the Lagrangian. I mean, this corresponding to the free particle. It depends only on x dot and L, x dot and lambda. Now there was yet another approach, another approach that was considered not so far in this lecture, but in your core QFT course 1, and that's called quantum field theory. What is going on? In this case, in the non-relativistic quantum mechanics, time was a parameter, x was an operator. In relativistic quantum mechanics, both time and space became operator, and therefore you have state vector that is labeled by for space time or the event. Here, so here both time and space becomes parameter. And they become parameter, and we have in this quantum theory, the operators are the field operators. Okay, and this is of course a space-time approach. And an example of that is Klein-Gordon theory. Klein-Gordon theory, which is basically a theory of free fields. Okay. Now, I will be talking about certain relations among these approaches. So these are the three approaches that we have considered in describing quantum mechanics. Some of them non-relativistic, some of them relativistic, and some of them space-time, some of them world-line, and some of them are, path integral, and some of them are standard Schrodinger theory. Now, the relations, and this is important to appreciate, these relations among these relations among different approaches. So non-relativistic world-line approach for field theory for free particle, one non-relativistic world-line theory for free particle. From there, geometric generalization we arrived at a relativistic world-line approach for free particle. And then non-relativistic space-time theory for harmonic oscillator. And it turns out that there is a mathematical analogy between this and relativistic quantum field theory. Relativistic quantum field theory for Klein-Gordon fields, which is free. And it turns out that this this one and this one are physically equivalent. This is what we would discuss today. One is that there exists an analogy, mostly mathematical analogy, between the non-relativistic harmonic oscillator and relativistic Klein-Gordon theory. We will spell out that analogy or correspondence, and also we will discuss how the two approaches that you are now familiar with, One was from the course 1, which is relativistic quantum field theory for the Klein-Gordon fields or free scalar field theory, and the relativistic world line theory using path integral approach. This one, where you get this result. These two are physically equivalent. This is what we would discuss. These two things we will discuss today.